So in this video, we're going to talk about two last facts related to tangent planes. For both parts of this discussion, it's going to be really helpful to recall the formula for the normal vector to our tangent plane. So let's recall little n is equal to minus z sub x minus z sub y 1. Okay, with that in mind, first thing we're going to do is just ask a question. And the question is going to be, where is a tangent plane horizontal? So here's our tangent plane parallel to the xy plane. And remember that the normal vector is a vector that's perpendicular to our plane. So normal vector could be coming up like this, or it could be coming down like that, but it's moving in the vertical direction because it's perfectly perpendicular to this horizontal plane. Now, if you think about the formula for a normal vector, the way we've defined the normal vector is we've said the z component is always going to be 1. So that means in our picture here, we can disregard the normal vector that's pointing down. And we can just say, okay, this is going to be our normal vector, then the one that's pointing upwards, just because of how the formula works. So we can say n will have to be, in general, could be some multiple of 0, 0, 1, but again, because we know that the z component is precisely equal to 1, we can say the multiple is actually 1. So the normal vector, because of how the formula works, is going to have to be 0, 0, 1. And therefore, we can conclude that means that the partial z sub x is going to have to equal 0, and the partial z sub y is going to have to equal 0. So to answer the question, where is the tangent plane horizontal, we could say the answer is any point where z sub x equals 0 and z sub y equals 0. So we're going to talk about these type of points a little bit more later on in the course. It's nice to just have that introductory question in our minds before we do that. Okay, so that's the first part of this video done. Second part of the video, we want to talk briefly about where does the formula for this normal vector come from. Okay, so let's just ask, why does the normal vector equal minus z sub x minus z sub y 1? Well, let's draw a surface sitting in space. So here's our surface, and what we're going to try to do is, well, let's focus in on one point and the tangent plane associated with this point. So let's say we've got this tangent plane, not necessarily sitting horizontally here, it's just any plane that comes in and just touches the surface at whatever point we're interested in. So let's try to find two direction vectors for this plane. So we're going to call them vector u and vector v. Okay, and then the idea from linear algebra is that the normal vector will end up being the cross product of the two direction vectors. So we're going to find these two direction vectors, u and v, that determine the directions of our tangent plane here. So we'll see how to do that in a minute. And then once we've got our two direction vectors, we're going to cross them together, and that's going to give us the vector that is going normal to our plane, that's perpendicular to our plane. Okay, so let's write down what we're doing here. U and v are going to be our two direction vectors for the tangent plane. All right, so let's focus in on the first vector, u. Let's define that to be the tangent vector in the x direction. All right, so notice that our vector u, it's not moving at all in the y direction. It is moving forward, so it's moving in the x direction, and it's also moving in the z direction at the same time. This tangent plane may be slightly tilted in space, so the z value may be increasing or decreasing as u moves forward. Okay, so let's zoom in on what's happening in the xz plane when we think about this this direction vector u. Okay, so let's say u looks like that. Because u is a tangent vector to our surface, in the x direction. If we take a step of 1 unit in the x direction, let's actually draw a triangle here. If we take a step of 1 direction, or 1 unit rather, in the x direction, the amount of change that we should be seeing in the z direction is z sub x. And that is simply just by definition of the partial derivative z sub x. Z sub x represents the rate of change of our function z with respect to the variable x. So when you change x, when you increase x by 1 unit, the amount of change that you're seeing in your z variable is z sub x. Okay, so from there, we should be able to write down actually the components of our vector u. So we're incrementing x by 1, just increasing, seeing a change of 1 unit in x. Y value is not changing at all, and the z value changing by z sub x. So that's one of our direction vectors for a tangent plane. It's giving us a sense of how quickly z is changing as x is changing, and now we've got the specific components of that vector u. So in a similar way, if we let vector v be the tangent vector in the y direction, we would find that the vector v doesn't move at all in the x direction. Let's say it moves 1 unit in the y direction, the amount of change we'd see in the z direction, z sub y. Okay, so now what we've got are the components for the 2 direction vectors for our tangent plane. So let's scroll back and look at our picture there. So we know u, we know v, and we know that we're going to get the normal vector for our tangent plane just by taking the cross product of those 2 vectors. So thinking back to the cross product from linear algebra, we're going to take u cross v, and you can check that this comes out to minus z sub x minus z sub y, 1. So if you don't quite remember how the cross product works, you can check out the next video for a little bit more detail. Thanks for watching.